Hi everyone, welcome to Drawing Hub. So this is Computer Graphics and Image Processing Module 1 Part 4. So in the previous video, we have completed refresh cathode ray tubes and its definitions. Now, next we have to look random scan displays and systems. Random scan displays and systems and also raster scan displays and systems. So first we will go through raster scan displays and systems followed by random scan displays and systems. Now when raster scan displays, the most common type of graphics monitoring employing a CRT is the raster scan display. In raster scan display, the most common type of graphics monitoring employing a CRT is the raster scan display based on television technology. Here we are using the television technology. So in a raster scan system, the electron beam is swept across the screen one row at a time from top to bottom. So in raster scan display, the electron beam is swept across the screen one row at a time from top to bottom. So from top to bottom, it is going like rows. As the electron beam moves across each row, the beam intensity is turned on and off to create a pattern of illuminated spots. Now, the electron beam will move across each row and the beam intensity will be turned on and off. So, this will create a pattern of illuminated spots. So, the picture definition is stored in a memory area. All these are included in the definition. Okay. Now the picture definition is stored in a memory area called the refresh buffer or the frame buffer. Now we have the refresh buffer. The picture definition is stored in a memory area called the refresh buffer or the frame buffer. This memory area, that is this refresh buffer or the frame buffer, holds the set of intensity values for all screen points. Stored intensity values are then retrieved from the refresh buffer and painted on the screen one row. So that is called, this is row, right? So this is row. And that one row is what we call the scan line at a time. So one row at a time. Now each screen point is referred to as a pixel. Now each point, this is referred to as a pixel or a pel. So pel is a shortened form of picture element. PEL, picture element. Now, the capability of a raster scan system to store intensity information for each screen point makes it well suited for the realistic display of scenes containing subtle shading and color patterns. So because of this property, it can be used, that is, the raster scan display can be used for scenes which contain the subtle shading and color patterns. Now, home television sets and printers are examples of other systems using raster scan methods. Intensity range for pixel position depends on the capability of the raster system. In a simple black and white system, each screen point is either on or off because only black and white color is there, right? Now, so only 1 bit per pixel is needed. Now, for black and white, we are using 1 bit per pixel is needed to control the intensity of screen position. For a bi-level system, a bit value of 1 indicates that the electron beam is to be turned on at that position. That is, 1 means if we are taking 1, okay, if we are taking 1 means it indicates that the electron is to be turned on. 1 turned on. And if the value is 0, 1 means turned on, 0. So 0, what does 0 mean then? It is off. Okay, that is clear. Now, additional bits are needed. So, that one was for black and white. Now, if it is for colored, the intensity variations to be displayed. If it is for more colored one, we can use up to 24 bits per pixel are included in a high quality system, which can require several megabytes of storage for the frame buffer. That will be depending on the resolution of the system. A system with 24 bits per pixel and a screen resolution of 1024 by 1024 requires 3 megabytes of storage for the frame buffer. On a black and white system with 1 bit per pixel, the frame buffer is commonly called a bitmap. For black and white with 1 bit per pixel, we call the frame buffer as the bitmap. And those having more, that is multiple bits per pixel, we call the frame buffer as Pixmap. Okay, that you will get into confusion. So, for 1 bit, it is bitmap, singular, right? Now, for multiple, more than 1 means it is having lots of pixels, so it is a Pixmap. Okay. Now, refreshing on raster scan displays is carried out at the rate of 60 to 80 frames per second. So, even raster scan needs refresh, right? So, for that, this rate, the refreshing rate is 60 to 80 frames per second. Although some systems are designed for higher refresh rates, sometimes refresh rates are described in units of cycle per second or hertz, where a cycle responds to 1 frame. Using these units, we would describe a refresh rate of 60 frames per second or simply as 60 hertz. At the end of each scan line, the electron beam. Okay, now when it reaches the end, the electron beam returns to the left side to begin displaying the next scan line. The return to the left screen after refreshing each scan line is called the horizontal retrace of the electron beam. This it is not here. Okay, and at the end, each frame displayed in 1 by 80th to 1 by 60th of a second, the electron beam returns to the top left corner of the screen to begin the next frame. So what does that mean? Here it is going to the right side. It is going to the right side. And then it comes back to the left side. This is what we call horizontal retrace. It is going horizontally, right? It is going horizontally. And it is retracing its path. It's going back to its path. That's why retrace, horizontal retrace. And then it goes back again. Then it is retraced, goes back again, retrace. Here. Now when it reaches the end, it has to go back to the top. And that is what we call as vertical retrace. So it is going back. This is vertical retrace to the top left corner of the screen to begin the next frame. On some raster scan systems and in TV sets, each frame is displayed in 2 passes using an interlaced refresh procedure. In the first pass, the beam sweeps across every other scan line from top to bottom. Then after the vertical retrace, the beam sweeps out the remaining scan lines. The interlacing of scan lines in this way allows us to see the entire screen displayed in 1/2 the time it would have taken to sweep across all the lines at once from top to bottom. Okay. Now this is an effective technique for avoiding flicker, providing that adjacent scan lines contain similar display information. So we have condition over there too. Now, raster scan display. This is the proper figure. See over here? This is the figure. You can pause the video and note it down. Then the horizontal retrace. See? The electron will go over there and then it will be retraced. It will retrace back. That is what we call the horizontal retrace. Then it comes back, again it goes. And when it reaches the end of the page, it goes back to the top left corner. That is called vertical retrace. This is the scan line. Scan line, horizontal retrace and vertical retrace. Raster scan displays, electron beam is swept across the screen 1 row at a time from top to bottom. As the electron beams move across each row, the beam intensity is turned on and off to create a pattern of illuminated spots. picture definition is stored in memory area. That is called refresh buffer or frame buffer. This memory area holds a set of intensity values for all the screen points. Stored intensity values are then retrieved from the refresh buffer and painted on the screen, one row scan at a line at a time. Each screen point is referred as a pixel picture element, or a PEL. At the end of each scan line, the electron beam returns to the left side of the screen to begin displaying the next scan line. Intensity range for pixel position depends on the capability of the raster system. In a simple black and white system, each screen point is either on or off. So only 1 bit pixel per pixel is needed to control the intensity of screen position. For a bilevel system, that is a byte value of 1 indicates that the electron beam is to be turned on at that position, and a value of 0 indicates that the beam intensity is to be off. Now, additional bits are needed when color and intensity variations have to be displayed. Up to 24 bits per pixel are included in a high quality system, which can require several megabytes of storage for the frame buffer depending on the resolution of the system. A system with 24 bits per pixel and a screen resolution of 1024 by 1024 requires 3 megabytes of storage for the frame buffer. On a black and white system with 1 bit per pixel, the frame buffer is commonly called as a bitmap, and for systems with multiple bits per pixel, the frame buffer is referred to as a Pixmap. The refreshing rate, called the frame rate, is normally 60 to 80 frames per second, or described as 60 Hz to 80 Hz. The return to the left of the screen after refreshing each scan line is called the horizontal retrace of the electron beam. And at the end of each frame, displayed in 1/80th to 1/60th of a second, the electron beam returns to the top left corner of the screen to begin the next frame. That is vertical retrace. This is a figure of interlacing scan lines on a raster scan display. This is a figure for that. Then each frame is displayed in 2 passes using an interlaced refresh procedure on some raster scan systems. In the first pass, the beam sweeps across every other scan line from top to bottom. Then after the vertical retrace, the beam sweeps out the remaining scan lines. Interlacing of the scan lines in this way allows us to see the entire screen displayed in one half of the time that it would have taken to sweep across all the lines at once from top to bottom. And we're having an architecture of a raster system with a fixed portion of the system memory reserved for the frame buffer. Now there is input-output devices, and we have the system bus. The system bus is connected to the CPU, the system memory, the frame buffer, the video controller. Now the CPU will pass information over here, and it is connected. The system bus is connected to the system memory and the frame buffer. This is connected to the video controller, which is also connected to the system bus, and finally it is displayed through the monitor. And in an interactive raster graphics system, in addition to the CPU, a special purpose processor called the video controller. See, we have a video controller over here, or the display controller is used to control the operation of the display device. A fixed area of the system memory is reserved for the frame buffer, and the video controller is given direct access to the frame buffer memory. Frame buffer locations and the corresponding screen positions are referenced in Cartesian coordinates. For many graphic monitors, the coordinate origin is defined at the lower left screen corner. The screen surface is represented as the first quadrant of a two-dimensional system, with positive x values increasing on the right and positive y values increasing from bottom to top. The scan lines are then labeled from y max at the top of the screen to 0 at the bottom. Along each scan line, screen pixel positions are labeled from 0 to x max, 0 to y max, and 0 to x max. On some personal computers, the coordinate origin is referenced at the upper left corner of the screen, so the y values are inverted. This is the basic video controller refresh operation. We have the raster scan generator. It is connected to X register and Y register. The X register and Y register goes to the memory address. The memory address to the frame buffer. And we have the pixel register. So the frame buffer is connected to the pixel register, then the intensity. Then the two registers over here, that is the X register and Y register, are used to store the coordinates of the screen pixel. As I told you, we have different coordinates of X and Y. So these two registers are used to store the coordinates of the screen pixel. The X register is set to 0 and Y register is set to Y max. Okay. The value stored in the frame buffer for this pixel position is then retrieved and used to set the intensity of the CRT. Then the X register, now it was 0, X register was 0. It will be incremented by 1. Once the process is done, the X register will be incremented by 1 and the process repeated for the next pixel on the top scan line. This procedure is repeated for each pixel along the scan line. After the last pixel on the top scan line has been processed, the X register will be reset to 0 and the Y register is decremented by 1. Now, pixels along the scan line are then processed in turn and the procedure is repeated for each successive scan line. After cycling through all pixels along the bottom scan line, Y will be equal to 0 because Y was decremented. The video controller resets the register to the first pixel position on the top scan line and then the refresh process starts over. To speed up pixel processing, video controllers can retrieve multiple pixel values from the refresh buffer on each pass. The multiple pixel intensities are then stored in a separate register called the pixel register and used to control the CRT beam intensity for a group of adjacent pixels. This is the similar image that we have learned before. That is the architecture of a raster graphics system with a display processor. We are having a system bus which is connected to the CPU and the display processor and the system memory. Okay. We have the display processor memory connected to the display processor. We also have the frame buffer which is connected to the video controller and the monitor. The purpose of display processor or graphics controller or a display coprocessor is to free the CPU from graphics cores. In addition to the system memory, a separate display processor memory area can also be provided. This is the character defined as a rectangular grid of pixel positions. Then the main task of the display processor is digitizing a picture definition given in an application program into a set of pixel intensity values for storage in the frame buffer. And this digitization process is what we call the scan conversion. Display processors are also designed to perform a number of additional operations and to interface with interactive input devices such as a mouse. We have problems which we'll do in the next video. Before that, we have to look the KTU notes also. The most common type of graphic monitor employing a CRT is a raster scan display. In this system, a beam of electron is moved across the screen. It moves from top to bottom considering one row at a time. As the beam of electron moves through each row, its intensity is alternatively turned on and off, which helps to create a pattern of spots that are illuminated. When each scan of the line is refreshed, it returns to the left side of the screen. This motion is known as the horizontal retrace. As a particular frame ends, the beam of electron moves to the left top corner of the screen to move to another screen. This motion is referred to as a vertical retrace. The picture is then stored in an area of memory known as the frame buffer or the refresh buffer. The buffer in a raster scan is that area that is responsible for containing intensity of the various points on the screen. The values stored in the buffer are then fetched and traced over scan lines one by one on the screen. Then this is about raster scan system, the figures which we have previously discussed. It's a simple architecture. The system bus, the input device is connected to the system bus, which is connected to the CPU, the system memory, and we also have the raster system over here, the frame buffer. Now, video controller and the monitor. This is a commonly used architecture. So this was a commonly used one. This is a simple architecture, but we prefer to draw the commonly used architecture. That is of the input device connected to the system bus. It's similar to this one. We have the CPU, we have the system memory, but we will also have a frame buffer which is connected to the video controller. Try to draw this picture on this one. Then the basic video controller, we have the frame buffer, the address memory, registers. So the Raster can generate a result. It is connected to X register and Y register. So initially X is set to 0 and Y is set to Y max. Then X will increase. Then after that Y will decrease. Now X register and Y register connected to the memory address to the frame buffer. Now this is connected to the pixel register. Horizontal and vertical voltage intensity. So we have advantages. Real life images different in different shades can be displayed. So Raster scan is used for real life images and different shade can be displayed. So different color range is also available in this. The problems we will do in the next video. So then bye bye.